Welcome back. Now we go for the package low rank QP. This is a package that comes together with VR statistical software to solve convex and concave problems. And we'll see how it approaches the support vector machine problems. Okay. This package actually implements the paper we discussed before by Fine and Scheinberg. It brings a full implementation, and of course, it is much better and faster than our previous code because it was optimized by maintainers and people cooperating to make it better. So we're going to start with a code I wrote for you guys. Actually, it is different from the code I mentioned here. We'll start with this linear svm.r. I decided to write beforehand for you, and I will compare the problem I have here. I have written actually this function with the one solved by the low rank QP package. I will open another R instance here, load the package low rank QP, and ask for the manuals of the function low rank QP. You see this function solves this particular problem. Minimize, and it's primal, and the dual is also a minimization. That's possible because we can just invert the signs of course, our objective function. Okay, that's why both are in minimization forms. I will go back to our previous slides, considering the last class. Yeah, I suppose those are the slides I need to consider. Yeah, oh, actually, we are exactly at the right page. Here we've got the primal and the dual problems, and here we've got how the package low rank QP approaches convex and concave problems. We can notice there is a great similarity in, of course, among all four problems, but there are like some dissimilarities that we need to correct. Just to show you, here we've got plus half alpha transposed H alpha, and that's the same as half of alpha transposed Q alpha. So our matrix Q will be here the matrix H. Here you guys have D transpose, which is a vector, of course, alpha, and here you guys might find, oh, there's nothing related to that here, but there is something in the dual form. In the dual form, so you're going to see that this is closer. Actually, this represents our dual SVM problem. Okay, here it is a maximization, here is a minimization. We're going to see there is a sign difference. So here you've got a vector of ones multiplied by alpha. And here, instead of a vector of ones, we will consider D as a vector of minus ones. So if I go to my code here, you see I define my vector D with a vector of minus ones. I've got M inputs, so M minus ones, multiplied by alpha. So this will change from a minimization to a maximization. And of course here, if it's positive and here is negative, both objective functions represent the same, while this is a maximization, this is a minimization. So it's okay by now. Here we've got A multiplied by alpha, and our A will be Y transposed, as you might observe over here. So in my problem, I define matrix A as Y transposed along the row, along a single row. Okay. Here we have to make this equals to 0, and here we have to make it equals to b, so b will be 0 as well. In my dual, I have a vector of zeros, a vector of c's, and alphas are in between that particular range. Here we have zeros, that's okay, but here we have u's. So u's will be actually a repetition of the value of the cost value c m times to make it valid for all alphas, of course. So that's how I adapted this primal problem solved by the low rank QP to solve our dual problem in our, of course, support vector machine, of course, from our classes, from previous classes. The dual over here has all similarities with our primal support vector machine problem. Take a look. H is again Q. Here we've got C transpose U, and U is of course a vector with all those C's as we discussed, and C's are C's. There is something else that we don't consider here, which is beta transpose B. But you guys remember our B is going to be 0. So this is basically vanished. So there's no problem. We have a such that, or I mean, of course, the constraints, Q alpha is H alpha, okay? Plus some A transpose beta, that's Y transpose B. So beta is of course this B for us. This plus C is this guy. This, of course, this vector C will contain is a one vector. It's basically this one vector. And this minus zeta in our scenario is actually this minus S. That's related to the slack variables as we discussed before. Okay? That's pretty much the same problem. I adapted here, as you guys might notice. I wrote SVM linear. I just brought the problem over here, loaded the package, and decided to call my function SVM linear. Receiving my input space, and in attempt, of course, to predict my output space, and define some cost function with 100 as its value. You guys can change it. Of course, this will adapt the interval for alphas. If you guys define some low value here, there's not much about possibilities for alpha, and that might provide terrible results for your problem. So you better decide using or adopt a large value for C instead of a smaller one. Okay, here I'm just counting up the number of examples I have in my matrix X, computing matrix Q. This is the linear kernel. You guys probably remember that Y multiplied by Y transposed, element-wise multiplication by X transposed provides my matrix Q. That, of course, for the linear kernel. We're gonna talk about the polynomial kernel still in this class, but that's next. And D will be a vector with m elements. I mean the same number of examples, of course, with minus ones. So I told you before, this D, what is D? Yeah, here, will contain minus ones instead of plus ones, because here's a maximization, here's a minimization. Here is right, it's plus, and here's minus. So it's just an adaptation in terms of minus ones to define this vector D to be multiplied by alpha. A contains Y transposed, B is equals to 0, and U is a vector of costs of C's. Then we can just call our model, just call this function low rank QP. And the function receives, take a look over here, this parameter vmat is actually h. In our case, it's q. Okay, I know this name is kind of strange because they defined as h and now it's vmat, but the others are the same. The others are pretty much easier to be used. D vector is D. A matrix is A. B vector is B. U vector is U. So at least those are easier to deal with. And here we need to define some solver, some method to perform the solution. We actually can use two methods, the LU factorization and the Cholesky factorization. This is faster, however, this is more stable. Both are used when we have a squared matrix, okay? When V is squared, when Q is squared in our case. Our Q is always squared, so we can use either of those, okay, either one. Here we have like some other possibilities for non-squared matrices. This is our scenario. I'm going to use Cholesky just to make it faster. That's all pretty much over here. I will return the model, okay? And here I came up with our classification. How is going to work our classification? We receive a model. Actually, I haven't tested this code, all this code together, but we're gonna try now. I provide my model. I provide my input space, my output space, and my new value to be classified, my new example to be classified. You probably remember that vector W is essential to find my solution. You guys probably remember this. I haven't written here, but let's write now. W dot product by some new example plus some B must be either equals to +1 to the closest point I have in my space, either equals to -1, and that actually depends on having the closest positive element and the closest negative element of my space. So over here, you guys probably remember how we computed W before. W was a result of a differentiation of the first Lagrangian function we had for the support vector machine problem. That is alphas multiplied by y's and multiplied by the input vectors. Of course, we have to compute that W dot product by an x nu. And that is the dot product of all this term, which is W by x nu. Of course, this is a vector and this is another vector, so I need to represent their dot product by using an internal dot product of my sum. So I have a sum of alphas, y's, multiplied by my dot products, okay? So this is the solution, a sum of a vector alpha multiplied by a vector y. Of course, this is an element-wise multiplication, and another element-wise multiplication in which I perform this product. This is, of course, the dot product of every input example I have in my space against x nu. And at last, I sum up beta, modulo beta. What is modulo beta? Remember, beta is this B. Take a look. This is actually the B we found in our formulation for this and this constraints. Okay, that's the classification. So here we have the full code for the linear support vector machine and how we perform the classification. Then I decided to write a quite simple example in which we define the sample size. This 100 will actually help me to come up with my input space. I decided to define my input space like this. I will start with a mean equals to -10 and -10 in a two-dimensional Gaussian function whose standard deviation is 1 in both dimensions, and I will come up with m examples, m instances, in this case 100 instances belonging to this bidimensional Gaussian function, and an additional 100 examples belonging to a different Gaussian function here, bidimensional, of course, Gaussian function, whose means are 10 and 10, and standard deviations are again the same. The first Gaussian will belong to the negative class, and the second Gaussian to the positive class. So I just called my SVM function, SVM linear function, okay? I get my model, and that model, this one, after running low rank QP, let's see how it looks like. I'll just return it here so we can manipulate it in our terminal instead of running the remaining codes. Okay, so just open R, load my linear SVM. Okay, then I will call linear test 1. This, let me save my model over here. So when I run it, it will provide, of course, the model. This model comes up with, take a look, this variable which represents my model comes up with my variables alpha. Again, alpha is this. Okay. Beta is actually this B. X's, of course, are here, and zetas are S. Okay, this lax we've got to make this equality codes. Okay. If you take a look at alphas, you see some alphas are more and others are less important. Actually, we've got 2 relevant alphas. If I plot this using PCH20 and CX2, you are going to see we have 2 support vectors in this solution. Those support vectors are the ones whose alphas are more relevant. That basically means that most or almost all points but 2 input points of our spaces are related to support vectors. So they've got the Karush-Tucker multipliers greater than 0, while the remaining ones are equal to 0. What I did was just this. I computed the mean value for alpha. Yes. So the mean is going to be very close to 0. And I just asked, okay, which are the alphas greater than that? What are the identifiers, the row identifiers, 80, 80, and 132? Those 2 numbers will compose my vector ID over here. And they will be used to come up with a very interesting plot. I will start with a Parm-Frau that of course will compose. I will have 4 plots, sorry. My first plot is this. Plot my space X, plot my classes, which are -1 and +1 summed up to 2, because if I try to plot a vector with colors -1s or 0s, R cannot plot it. It's going to hide basically those points. When I sum up 2, -1 is going to become +1, and +1 is going to become +3. So I will have colors as black and green. PCH20, CX2, and I will plot this on top of my plot. Dataset and support vectors in red. So in red, using points, I will plot, take a look here, color red, just my support vectors. whose IDs have alphas greater than the mean alpha, the average value for alpha. I will start adding up a locator here so we can see the effect of this code together. I'm gonna run once more, let's see, and now, yeah, running my function. And now, of course, you guys can see the support vectors. This is the negative point related to the, that's going to represent a support hyperplane, like a sidewalk over here. And this is a positive point related to my support hyperplane. It's going to be like this. Okay? And of course, my hyperplane will lie inside this region, okay, at the middle of the region. When I click here, something is going to happen. Let's see what happens. Of course, by clicking my locator, I will have another plot. At this point, I don't want to click, I just want to close it. I will have a second plot. This is our second plot showing the values of x's. What is the meaning of x's? The greater x's are, the more relevant they are, the greatest was the correction I had to come up in this quality constraint. That basically means the greater is my class overlapping. The greater is my class overlapping. That's really, really interesting and really important, as you might notice. So I will plot, I will reload my code like this and plot once more. Run, of course, and plot. You guys will see now my support vectors. Of course, my sample and how many x's are relevant, but they are very close to 0. This is 10 to minus 17. 2 points had some relevance associated to the values of x's, but that relevance is really close to 0 at the end of the day. So we haven't actually needed any kind of contribution because there's no class overlapping in my space. What's going to happen if I had some class overlapping? We're going to see that x's will be really large. And this is our classification. Oh, this is not necessary because I wrote that in the other function. So here I just came up with a sequence of values in between minus 15 and plus 15 with 1000 values inside that range. And I decided to write 2 fors. One for to vary a scalar value x1 in that particular range L, and another x2 in the same range, so I can compose x1 and x2 to form my x new to be classified. This is the point, the example I will be classifying. Here I just came up with a counter with an index I and j to add up in a matrix M. Actually, I forgot creating this matrix. It will be a matrix at the beginning with zeros. It will contain 1000 rows and 1000 columns, just because I decided to segment this range from minus 15 to 15 in 1000 values. So I'll have this from the first to the 1000th, and this also from 1 to 1000. And of course, I will fill out my matrix. After filling up my matrix, I will plot it, applying a sine function. If I apply a sine function, I will have +1 and -1 as results, and my image will be an image with a very clear hyperplane crossing the positive and the negative regions, dividing, of course, and this will be something like a gradient hyperplane. That's what I expect. And this is actually, this is not necessary. This is the return list with all x's, y's, my model, and my matrix M if you guys wish to plot again or assess it or use it later. I will reload my code once more and run it. And now you can see, let's see, like this. So yeah, it is going to plot. So nice. Yeah. Plotting again. Yeah, this is a typo. Yeah, that happens sometimes with R. If I reload my chart, probably it's going to be better or worse. As in here, let's see. Yeah, still, yeah, doesn't matter. My sample, my support vector for the positive label and for the negative label. I have some relevance for x's, but that's not really important because that's 10 to minus 17, so there's no class mixing. Here is exactly where my hyperplane lies on, because I'm varying my space from minus 15 to plus 15 and minus 15 plus 15 as if it were those axes, those original axes of my space. So my hyperplane lies here. This is a gradient view of my hyperplane, just noticing that here we've got some negative values and here some positive values. That's actually not necessary, but yeah, if you guys want to test. And you know what? We could change this linear test to adopt the means. So it could have something like this for the Gaussian means. Yeah, we can start with minus 10 and plus 10. And here I could use something like this. The first mean will be for the first Gaussian function, and it will be the same mean, of course, for both dimensions. And here the second. What is nice about this is that now we can try some class overlapping. There's another point. We could adapt the standard deviation. I'm going to set up the same standard deviation. So here it will be SD and here SD as well. And over here to SD, standard deviation. Running, reloading my code and running now. We could try maybe SD equals to 1, but the means could be minus 2 and 2. Wow, that's much more interesting. Why we've got like an additional support vector over here? Just because there is some class mixing happening. If I increase that, of course, take a look at the x's. There is like some increase from minus 17 to minus 13, but it's not that relevant. However, if I change the means to minus 1 and 1, wow, this is a relevant class mixing. Several points had to be considered to represent my my support hyperplanes. If you consider x's, now x's are really large. We've got like some x's equals to 3, to 1.5, to 0.5, so they are really relevant. That happens because we have some class mixing. So if you guys want or wish to employ the support vector machine to analyze your space, you can take those x's into consideration to analyze your space. There is something I wasn't thinking to talk about, but I think that's interesting. After running, you guys have your model here because I'm just returning the model. And inside you have x's. Take a look. You know what's interesting? Look for von Neumann's entropy. The von Neumann's entropy is basically an entropy exactly like the Shannon's entropy, but that's for the eigenvalues. Those eigenvalues I could consider those elements x's as corrections in terms of variances I have in my space. So I could use those values like this. So x's multiplied by log of x's, but that requires some normalization. So this should be represents something like a probability. So this should be divided by the sum of x's, and this as well by the sum of x's. And by summing up all that, I would compute with a negative sign my entropy, my space entropy. I'm going to enter here. It's going to represent some mistake. Doesn't matter. Why? Because I haven't used m model c. That's the name of my variable actually. M model c, and of course over here m model c over here m model c. The greater this value is, the greater is the uncertainty of my space. What happens if instead of performing this test using the means -1 and +1, I use -2 and +2? I will have a smaller class overlapping. That, of course, affects my x's. And of course, when I compute my uncertainty, take a look. Wow, it's greater. Oh, yeah. You know why it is greater? Because I cannot actually normalize this. That's my mistake. Sorry, guys. I just wanted to show you something new, but I cannot normalize. I can't just because, of course, here I'm closer to 0. When I normalize, I'm going to make all those values more relevant. So I must do something like this. So in this case, I will have this as my approximated entropy, just an approximation, so to speak. And of course, if my space has a greater class overlapping, like this, let's see what's going to happen with my attempt of entropy, okay? Just to be fair. Oh, it's going to change the value. Actually, it's going to be, it's going to be negative just because my values are not normalized. Yeah, anyway, I need to perform some sort of normalization over here. Okay, let's try some normalization. If I started, I'm going to go up to the end. You know what? I'm going to do this. Call this as xi. Normalize like this. Xi is going to be the value of xi minus the minimal of xi divided by maximum value of x's minus the minimal value of x's. This is going to return values in between 0 and 1. I suppose this is going to work now. Let's see. So it's not model here, it's just xi. Let's see. Okay, because there are like some zeros. And of course, my log, when I compute the log for values equals to 0, it's not going to compute. So I should consider something like this. Consider every xi whose value is greater than 0. So consider every value for xi whose value is greater than 0. Okay, so I've got like some value 8.9 for this space. Let's try again. So running for -1 and 1, it's running. Now after running, I'm going to get all my x's and bring those to my new vector xi over here. I will normalize them, Let's see if this works. And then compute something similar to a von Neumann entropy. Okay. What happens if, of course, my space is like this? It has smaller class overlapping. I expect my uncertainty to be reduced if my measure is right. If it's not, we can adapt, of course. So C's will receive this, and then normalizing, and of course computing something similar to the von Neumann's entropy, which was reduced as expected. What happens if, again, I try a very separated sample? 10 and 10 plus 10 and minus 10, those like have no class mixing. What's going to happen when I compute get my x's and normalize, then in range 0, 1, just to make sure that my logs will reflect some sort of uncertainty. Oh yeah, no, you see, that normalization doesn't work like that easy. Actually, we need to take a look at those values. There's no other way, no problem. You guys take a look at those values. If they are small, you know. If they are great, you know what to expect. Actually, you know what's even better? You can just sum up. Yeah, just sum up C's. So the greater C is, the greater is the uncertainty. In this case, the uncertainty is really small, as you might notice. If I run something like, okay, there's going to be 0.5 and plus 0.5. Oh yeah, the sum of C's will be really, really large. Take a look. Impressive. Just because we have a very large class overlapping. So just sum up C's, okay? Actually, this sum of C's is what we consider in our formulation. Okay, I was just, taking a different path over here. It doesn't matter. Okay, so now, you know what? I prepared an additional code for you. I decided to start with the formulation of a polynomial kernel for you. This is my code writing a polynomial kernel. I just called my function SVM polynomial, as you guys can see. Let's bring this. Yeah, okay, this is my Q matrix. It's Y transpose Y, element-wise multiplication by X transpose X. If you guys consider that just this, you've got the linear kernel. This is the linear kernel. And what can I do at this stage? If I add up some coefficient here, I decided to call as coefficient 0 because that's a typical name packages use. Some packages like libsvm, like some other R packages as well. And there is also the possibility of changing the scale of our dot products by multiplying by some gamma to make it like smaller or greater, of course. And those gammas are greater than 0. Otherwise, if it's equals to 0, I'd be considered just coefficient 0. And the whole classification, what makes like no sense. If it's negative, what's going to happen? My problem will not be convex anymore. It will invert my problem. We're going to see that later. I can show you guys. And if coefficient 0 is equals to 0, this is a homogeneous kernel. We'll discuss later. And if coefficient 0 is greater than 0, it's going to be a non-homogeneous kernel. Non-homogeneous kernel. If it's smaller than 0, it's going to somehow reduce the relevance of the dot products and make all those points closer in my space instead of separating those, have been making those points closer, bringing those points closer. If I consider some degree over here, like this degree, yeah, that's nice. Yeah, maybe I could just do like this to fit in a single common line over here. By considering this degree, if degree is equals to 1, this will be a linear kernel. It could be a linear kernel, a first order polynomial kernel is a linear kernel. Okay, it could be a linear kernel homogeneous if coefficient 0 is 0 and non-homogeneous if it is different. And of course, you guys can try some gamma values to see what happens. If it's a second order polynomial kernel, degree will be 2. Third order polynomial kernel, degree will be 3, and so on. And you guys can add up some coefficient to make our kernel non-homogeneous. What is the effect? The effect is kind of easy to imagine. I will discuss in details, but a second order polynomial kernel with some coefficient basically means that my space will contain every second order feature as well as the first order features. So it's going to bring the first order space together. And the third order non-homogeneous is going to bring all features from the second order and the first order spaces. Okay, that's something. That's our code. This is our classification, and there's something different over here, I suppose. Oh, no, sorry guys, I just rewrote here the linear test. Actually, you don't need this linear test over here. It makes no sense. Okay. And here is how we're going to classify. The code is basically the same we had for the linear support vector machine solving our problem. However, there is a difference, as you might notice. Here we received some gamma. I just decided to employ my gamma in my kernel. I decided to employ some coefficient in my kernel, and I decide to employ some degree in my kernel. So every time I compute my dot product from a given example I have in my sample against some new example to be classified, I have to apply that particular kernel. Otherwise, it's not going to work. So if here I employ some second order polynomial kernel, but here I apply in my classification process a linear kernel, no, it's not going to work. It's not going to produce the result or the effect that it should have produced. So if here I decide to apply some kernel, here I must use the same kernel. Of course, we could get like, you know what? I think it would be like just easier if instead of just producing the model here, I could just return gamma together in my model. I could also return coefficient 0 in my model, and I could also return in my model the degree. That makes everything easier. You know why? Because now I can just, in my polynomial classification, I don't have to pass all those parameters along. Just my model, and here I have model dollar gamma, and here I have model dollar coefficient. Just easier, right? And here model dollar degree. And of course, I have to sum up my beta, and that's my B. You guys probably remember. And this is my first test using my support vector machine, solving my polynomial kernel. Okay, so here we've got this. I just decided to come up with a very nice example. You guys can take a look at this package later. It doesn't matter at this point. What matters is I just used this package to employ this function embed because it helps me to build up a more complex classification problem. I will plot my problem and use a locator here so you can see my sample, how my sample looks like. I will save this, load my code, that is going to be polynomial SVM, and then run polynomial test 1. Polynomial test 1. Let's see. Yeah, this is my space. Take a look. It's much more complex. I've got a bunch of negative examples, and around I have the positive green examples. And when I click on top of this chart, of course, I will unlock this locator and run the following steps. I just remove the locator now and perform the same as before. Oh no, I don't want to see that at this point. Okay, I will run my SVM polynomial as before. I will get the IDs of every Karushkin-Tucker multiplier greater than the average value, and those will be the ones considered to represent my support vectors, my support hyperplanes, if you guys remember. Then I will plot exactly those points. You know what? I think we better use the locator, because now we're gonna, when I click, we see the red points just right after. I think that's much nicer in my opinion. Then we could use another locator here, yeah, just to make this like step by step. Then we are going to plot x's, and you guys can see if x's are large or small, and of course if they are large, you know there is a greater class overlapping. And then I just divided my space from -1/2 to +1/2 in 100 values, built up a matrix M, and performed the classification as before. Now we don't have to perform the classification passing or giving all those parameters, all those arguments for my polynomial classified. I haven't tested. Let's see what's going to happen. And then I will plot my image, of course, with +1s and -1s in the first one, just to define what is going to happen with my hyperplane. And the second is going to be a gradient-like hyperplane, just with lots of transitions, soft transitions in terms of colors. Okay, running. Okay, that's nice. That's my problem. I'll click here. And now, of course, I'll have my x's. Yeah, x's are here. Sorry guys, I'm going to run again. I forgot about the red points, red dots over here. Because when I click, we're going to see which are the support vectors. Clicking, take a look. One support vector here, one another here, and another here. Wow, that's so nice, so interesting. When I click again, we're going to see x's. And take a look at the x's. They have no relevance, 10 to -15. So if I sum up, of course, forgot to save, making a model here. Let's save like this. As I click now, and then we can sum up. Like the sum of all x's is almost nothing. So there's no class overlapping. We know there's no class overlapping. And this is the hyperplane we've got. The hyperplane is exactly here. So nice, isn't it? Isn't it? And this is a gradient point of view about this hyperplane. This is easier to see, of course, where the hyperplane exactly lies on. Okay? What happens if I increase? I think I defined like some possibilities. Oh yeah, I defined some standard deviation. I'm going to increase my standard deviation to 0.25. And you know what? Before that, I will increase, let me close this. I will actually increase the number of examples to like 500 examples. Wow. No, that's just impossible to run. There is such a class overlapping. Makes like no sense. No way, guys. It's not going to work. Of course, I prefer to stop this and try maybe before increasing, I'm just going to increase m, yeah, because the standard deviation is going to affect a lot my problem. Yeah, that's much more interesting at this point. If I click, we're going to see red points. Clicking, red points. Those are the support vectors. The smaller is the number of support vectors we have, the better is the separability. That's another criterion you can use to understand if your space is well separated by your kernel. That's interesting, isn't it? If I click again, I'm going to see the x's, and just 2 x's are relevant to make some corrections. That's okay. So we've got this hyperplane, and of course the result over here. Of course, I don't really remember standard deviation we used is here. Okay, we could increase it. Actually, you know what? I think that this guy over here should be a fraction. Yeah, actually, this is the way I decided to run my problem over here, guys. Sorry. This should be something like multiplied by, let me try something here. Multiplied by 1.1. Let's round this. I know you guys don't understand what I'm doing at this point, but it doesn't matter. This is just the way I decided to run, to coming up with a very nice classification task, just to make it like more complex. I wanted, of course, to make it more complex. Let's see what is going to happen here. I think this is maybe it's going to make our problem like more interesting to be visualized, at least in terms of visualization. Oh yeah, 500. So clicking, we're going to see the red points. 1, 2, 3. Clicking again, x's. Not that relevant. If I sum up x's, yeah, nothing. Hyperplane and gradient view of that hyperplane. Of course, now I will increase the standard deviation to 0.1. Oh, that increased at least the variance of my space, but my hyperplanes are still like 4 hyperplanes, so my x's will be small. And of course, no class overlapping. Almost no class. Oh, no class. 0.2. Wow, there is a relevant class overlapping now. Take a look over here. We're going to have like many red points. Clicking. Wow, several support vectors. Clicking again, x's are more relevant because now we've got some class overlapping. Okay, summing up x's. Oh yeah, they're much more important, much more relevant now. I'm going to increase the standard deviation to 0.3. Take a look what's going to happen, because now I've got like a green point inside here, which are going to be my red dots. Oof, so many red dots, so many support hyperplanes, support vectors to define my hyperplane. Take a look, even greater, those x's. My hyperplane, and why this hyperplane is like a Gaussian? Because when I convert this space, this bidimensional space, to a 3-dimensional space using my second order polynomial kernel, it's going to perform a Gaussian-like cut, a Gaussian-like division in my original space. We'll discuss more about that. And summing up x's again, oof, even great. greater. Yeah, it makes complete sense. Guys, that's all for now. I just ask you guys to try to re-implement all those codes. And let's see what I expect for the next class. I will write another example. And here we could, you could have like, if now we have a linear SVM and we have a polynomial SVM, we could have a Gaussian SVM. And we could also have a sigmoid, sigmoid SVM. I think that's a name. Yeah, I suppose that's a name. Yeah, we're going to check it out later. So after that, we're going to have like the most relevant types of kernels to employ. And then we're going to learn when and how to employ those. Okay? See you guys.